While you're having dessert and coffee, I'm going to take this opportunity to introduce our keynote speaker. So as they say on WestJet, let's get this Boeing going. David Kasik is Boeing's Senior Technical Fellow in Visualization and Interactive Techniques. He's pursuing new ways of using visualization for huge amounts of both geometric and non-geometric data. Dave has worked to make 3D geometry available to the entire Boeing user community. I'd like to tell you about some of the ways that he's doing that, but I haven't a clue, so I'm going to delegate to the man himself. Please take the time to read Dave's impressive bio in your program, and hear now from Boeing's offices in Seattle. Welcome, please, David Kasik.
All righty then. Well, thank you for staying awake during lunch. So I have to give you my first obligatory warning. I taught a class in Australia a number of years ago, and I got some really rave reviews, except for one person who described my voice perfectly. He said that Mr. Kasik's voice is of the type that is wonderful, should never be placed after lunch, because he really puts people to sleep. So try not to listen to the intonations, try to listen to the message. And in order to recapitulate the message, recap the message that we've heard so far in the conference, starting with Bob's talk yesterday, with Shang Yu's talk this morning, and the other talks, aside from touting the capabilities of BIM, what have been the two major themes that you have heard in all the talks to date? Anybody want to volunteer something? We'll see if you can talk with your mouth full. There are two words that I've heard repeated that I've repeated over and over. What's one? Money. Pardon? Saving money. Saving money. That's two words, but no, actually not. From a thematic perspective, one thing that you've heard is data. Okay, Bob really hammered on big data. Everybody has talked about the ability of people to make decisions and gain business insight with data. The second is visualization. And I'll talk a little bit about those things as I go through this presentation, and I'm going to try to go as quickly as possible because I have some dessert to cap off your dessert. Okay, so we'll talk about that in a minute, and we'll try to get the green button. The green button is not wanting to work. So this is here we go. So let me tell you a little bit about why I'm here. It's been great to see people use samples of Boeing commercial airplanes. Boeing builds a lot of really cool stuff. We thank the Canadian government for choosing some of our products as well in terms of transports, the C-17s, the Boeing helicopter purchase that was the MHLH helicopters that Canada bought. We're great partners with the Canadian government and the Canadian people. But the reality is that Boeing has some of the craziest technology possible in order to do our jobs better and to both provide the best defense systems as well as the best commercial transports in the world. We do everything. We do basic physics. We do more networking than you can possibly imagine that are both onboard our products as well as making conventional networks work for a workforce of 160,000 across the world. We do real-time and traditional computing systems. We do material science. We like composites, among many other things. We do natural language analysis. I'll talk about some of the reasons for doing so. If you have a technology that you like, an aerospace company of the magnitude of Boeing has it in that company at somewhere. I describe what we do in terms of data rather than big data is that we generate terabytes of data because you can get really afraid with the amount of data that we do in fact generate, and I'll talk about that at some length in one segment of this presentation. And we are working with advanced and visual analytics techniques to gather more business insight. So it's another one of these overloaded things. BI, right, talks for building information in this context. It talks for business intelligence. It talks for business insight. There are lots of meanings of the word BI. And so in this context, expand your notion a little bit that it's more than 3D modeling, and let me tell you a little bit about that. So let me tell you a bit about me first before we talk about the technologies. I'm a senior technical fellow at Boeing. That means that I've been around for a long time, and some people think that I've done some things. There's a computing group, so everybody's been confessing as to what their background is. I'm a computer scientist. Any other computer scientists out there? Very few. I'm in the minority on this one, so that's fine. But it's really fun to come to events like this and learn, because there are things that I'm learning from listening to all the talks. There's a computing organization called ACM. I'm a distinguished scientist for them. I'm a member of an editorial board. I've been involved with computer graphics for a lot of years, since roughly 1969. And I have a reputation around Boeing. I'm not a big fan of virtual reality. I like the democratization of computing technology, the ability for lots of people to gain insight from three-dimensional representations, much in the same way that we've been talking about it in BIM today. And I didn't coordinate this with Dr. Wang. I am an advocate for augmented reality. There's a huge upside for augmented reality. We just haven't realized it as yet. There's a lot of work still to do, so there's lots of room for your assistance in making augmented reality in both the building industry as well as industries like aerospace, automotive, et cetera, use virtual reality, or augmented reality better. And I'm also a broad proponent for democratic use of visualization for both geometric and non-geometric data. And I'm going to talk about both of those things today. Boeing has a long history with computer graphics as well. In fact, the term computer graphics was developed and invented by a fellow named Bill Fetter in 1960, who was a Boeing person. He also invented the first man model, the first human model, computer-based human model in 1964. We've done a lot of work in all sorts of things, including, as Dr. Wang noted as well, we invented the term augmented reality in 1990 with a fellow by the name of Tom Caudell. We've done work in fractals. We've done work on all sorts of crazy things. You wouldn't think that an aerospace company would do that. But aerospace companies push the boundaries. And in many ways, we have to push the boundaries in ways that are unexpected. And that's a big deal, because they are unexpected. We get involved with technologies that push computing to their limits. And we'll talk about a lot of those limits towards the end of this presentation. There are two things that I will be focusing on in terms of specific technologies. One is visual analytics and how that is applied to non-geometric data, and massive model visualization that starts dealing more with the three-dimensional data and how scale can truly get impacted and really become far more, our current computing technology is far more amenable to that scale than it used to be. So off we go. You've heard this message a couple of times. Bob talked about it last night. Those of you who don't know, who aren't in computer science, so this is Moore's Law. A fellow named Gordon Moore basically talked about transistor capabilities doubling in processing power every 18 months and reducing the cost in half. It's an unbelievable trend that has started in the late 60s and has continued through today. What's kind of interesting is that the data volume has actually increased probably greater than that rate, because we're really good at generating junk, right? Anybody who's read lots of information on the internet knows that you have to use some sanity in order to interpret what's there. You can't believe everything that's written. But we have this problem. We've got this brain, right? And our human capacity doubles once, maybe in a really long period of time, maybe 10 to the 7th or so months. We're talking about exabytes in 2006. We're talking about zettabytes in 2011 and 2012. Just to give you an idea of what that context is, a zettabyte is 10 to the 21st bytes. The amount of words that people have spoken is less than a zettabyte, ever. So we're just adding a very small amount, but we keep generating data a lot faster. The most important part about data analysis And this is something that at least in the experience that I have at Boeing, is very often misunderstood and misrepresented. Because what happens is that there are a number of different things that people can do with analysis, and I describe 8 different patterns that people actually do. They range from situation awareness, so you do that in a battlefield. You want to understand everything that's happening around you. You want to understand exactly what's happening with the square kilometer array at University of Calgary. That is something that you are sucking that data in and trying to monitor and change what's happening. There's a less onerous version that is tracking invisibility. You want to understand where parts are. Reza was talking about parts being fed into, was talking about his factory in terms of building houses. You have to understand how the supply chain works, where parts are, where you have shortages. So you want to get dashboards and things like that involved. One of the things that Boeing does a lot of in this particular case is understand, why does something happen? What is the cause that caused a specific function in a building to fail, and how can we correct the root cause instead of just flipping the switch back and resetting the system, because you know what? It's likely that it's going to happen again. So tracking through data to find that cause is a big deal. We wind up doing hypothesis testing. I actually think there's a whole lot to be gained by the scientific method, except not the Wired editor who talked about correlation that Bob referenced yesterday. The reality is that one of the things that we do well as humans is that we generalize from hypothesis and previous patterns so that we can reapply that knowledge to other problems. And so that we don't have to just gather data arbitrarily, and we can actually make some insights and do the right thing. That's one of the things that I think the building information modeling winds up doing, is that you can do the right thing at the beginning. Okay, there were testimonials about how that happened. Boeing does that as a matter of policy and a matter of course, and has done so for about 25 years. You can prevent occurrences by detecting anomalies, doing correlations. A lot of work on doing prediction and forecasting. Predictive analytics is a big buzzword to try to figure out how to do that forecast and stock supplies appropriately. Boeing does huge amounts of what-if studies. If you think about the engineering job that you do in order to build an airplane or an aerospace product, you wind up trading off. You try to figure out if the loads are correct, how to change those things. You try to do all sorts of things in order to make sure that you have the right design done before you start cutting metal, before you start building it. And it turns out to be a really big deal and a highly, highly complex sort of thing. We do it for computational fluid dynamics. One comment for you, Bronco, if you're still here. Airplanes are really flying ships. There are water lines. We have aft, yaw in terms of directions. Because in reality, what airplanes wind up doing is just basically moving through a different liquid, and that turns out to be air rather than water. So all of the basic design techniques that actually happen in the aircraft industry are from lofting techniques from shipbuilding. And it turns out that is a fascinating study in and of itself to understand how the airplane design process started and how those processes and strategies worked in order to get airplanes to work efficiently. Finally, never forget that one of the really difficult analysis tasks is to figure out how to summarize results so that somebody other than the analyst understands what you're trying to tell them based on the data that you've analyzed. And you have to communicate, I think the point that was made earlier today, that you communicate, both to your colleagues, to people up the chain, to people who are in the general public. It turns out to be a really hard thing to do. There are tons of tools and techniques. I'm not going to go through all of these here. Instead, what I'm going to talk about is visual analytics as an emerging class of tools. And you can map all sorts of different types of analysis types as the rows to different named tools that are the column headers. Again, this is something I won't go into in this presentation. What I'd like you to consider is where the X's are. Anybody see a row in which X's are all across, are in every, there's a column that has an X for every row. Very simple message. If you think you have a tool in doing analysis or modeling or whatever that is good for everything, I'd love to have some stock in that, because then I could retire. One doesn't exist, at least in the knowledge that I have to date. And one of the things that people have a tendency to do in the analytics space particularly is say that I have a tool, it is good for everything. So if I have a tool that can alert me that somebody in the back is falling asleep, anybody asleep yet? No, not yet. This is good. This is good. I'm doing all right. So, but the deal is that if you have a tool that you think is good for everything, you think you have a tool that is good for alerting me that somebody is falling asleep, I could also predict, I also want to use that same tool to predict that something's happening. That doesn't happen. Okay, so be careful when you hear salesmen tell you that something is good for everything. It just isn't there yet. I'm going to go through these in terms of understanding what types of data visualization there are in the non-geometric case. There are three basic parts. One is automated reports. Second is information visualization that Ed Tufte, if you've heard of Ed Tufte, has done a lot of work in. There are a whole series of books on the display of quantitative information. There is a special class of visual tools that dominates the world. And I'm curious, how many people are in here are Excel jockeys? And your business does huge amounts of work based on Excel. I'll argue that it is probably about 90%, easily, because Excel is the dominant analytics and visualization tool that exists in the world, that in the marketplace today. Last but not least, I want to talk about this field of visual analytics that looks at not only numeric data, but also tries to gain insight from text. So these are automated reports. Nice pictures, you generate them on some frequency, once a day, once a week, once a month. People pour through the reports and hope they can run the business better. Information visualization tries to communicate more about a situation. The classic is the image on the right from John Snow's analysis of cholera outbreaks in 1854 by plotting the location of cholera outbreaks and water pumps in the city of London in 1854. He determined that the outbreaks of cholera were isolated around certain pumps in the city of London, and all of a sudden people realized that cholera was a waterborne disease. Excel is in a class by itself, as I already mentioned. You can do just about anything as long as it's a histogram, a line chart, and you have some time and patience to figure out how to plot the stuff. Visual analytics is a little bit different. There's a formal definition that basically inserted one word into the vernacular of what is visualization and about the visual interfaces, and that's interactive. The idea is to allow people to explore data, complex data sets from multiple data sources, interactively and dynamically. Okay, there's a whole bunch of literature on it, and I've been involved with developing the original research agenda. It's really fun. It's really fun stuff. If you like the idea of being a data scientist who pulls data from different data sources, explores it, and then tries to answer questions that somebody who is a subject matter expert can pose to actually gain more insight for that thing, in that particular problem. Lots of players in the visual analytics world. It actually started in the U.S. Department of, in the U.S. intelligence community, because we had this event called 9/11 that I think many of you remember, and certainly many of you in Canada helped. A whole bunch of stuff in the U.S., in Europe. There's industrial activities at Boeing, Bank of America, Procter & Gamble, and others that has started. It's technology that you should pay attention to for understanding this non-geometric data. And what you have to understand is when you're starting to define the attributes in the data that's associated with complex three-dimensional geometry, all of a sudden you're starting to get lots of non-geometric data that's associated with that. And you can take different cuts at that data using a different type of tool set over and above 3D visualization and query. There are lots of people trying to make money at it. Again, it's a list that I won't go through in detail in the interest of time. Larger companies are starting to notice. The big players right now are IBM, SAP, SAS. Oracle is trying to get into the game, and Microsoft, of course, is interested. It turns out that Boeing is doing a lot of work in this area in terms of both implementation and in terms of research. And what we've done is we've partnered with a number of Canadian universities, specifically Simon Fraser, University of British Columbia, and Dalhousie, as well as universities in the US, Stanford, University of Illinois at Urbana-Champaign. We have our own folks who are working in text mining specifically. I'll give you some examples of what text looks like, because it turns out that there is huge amounts of information encapsulated in text data. And the language that gets used in a specific is highly discipline and industry specific. So you pay attention to things like the building industry has its own vocabulary. You don't necessarily have to admit it, but the building industry has its own vocabulary. Aerospace has its own vocabulary. Pilots have their own vocabulary. And the most fun are the maintenance techs from around the world who speak in flavors of English that are not necessarily understandable by anybody, including me. We are trying to transition the technology into use. So Boeing is involved in this because we are trying to improve our business by gaining more insight. Okay? From a Canadian perspective, we're working with industrial participation and gaining some offset credits for working with the Canadian universities. It has been a clear win for both Boeing and academia. And I'm going to talk about two specific examples that deal with things that actually affect, in some interesting way, all of you in this room. First is the notion of bird strikes. Okay, we were talking about that. Actually, Amr from CCCT was describing an incident in which his airplane had to turn back on its route to Calgary a few weeks ago because the windscreen shattered. And it turns out that things like birds can actually run into windscreens, probably not at that altitude, but there are bird strikes that happen all the time. Boeing has on staff a person who is an expert in bird strikes. How about that, huh? Talk about a cool job, right? You get to look at what the entrails of birds look like, and it's called snarge. That should really make you happy after lunch. But you realize that most of those bird strikes are unreported, and we're talking at $2/3 of $1 billion in terms of yearly damage to aircraft fleet. And it turns out that Boeing's goal in terms of airplane safety, and why we have this guy on staff, is that Boeing's target is to have airline safety, and this includes Airbus, it includes all of our competitors, to have that safety record at 10 to minus the risk at 10 to the minus ninth. And Roger was describing this last week at another meeting I was at, and he said, well, you know, the chances of the sun not coming up tomorrow are about 10 to the minus 14th. So the idea is to make airplane travel as safe as possible, and we have to gather data from lots of different data sources. So it turns out that what we wound up doing is enlisting the help of a student intern from Simon Fraser named Andrew Wade. He's the guy who has more hair in the picture. So Andrew and Roger sat down next to one another and actually went through analysis sessions using these visual tools to look at these multiple data sets to answer specific questions. And lo and behold, they looked at things like this report that has fascinating verbiage in it. You've got ENGs in it, you've got faux confirmed, all sorts of things that varies because the quality of text varies on the person entering its basis and his or her ability to type. Here's a specific example. This is multiple ducts that were hit an aircraft at 12,000 feet. And among other things, Roger and Andrew came up with this image that was actually that actually made it into the Boeing pilot training manual, because it tried to alert pilots that they need to pay attention to bird strikes not only during the day, but they have to pay attention to night. And if you look at this on a year-long basis, this was done at an incident for a year long. But if you look at it over time through all the seasons, why do you think nighttime? Anybody have a quick idea on why nighttime causes bird strike problems? Migration, exactly. And the top of the list in terms of problems turns out to be the Canada goose, because they also calculated the kinetic energy from a bird strike, and large flying objects with long necks called Canada geese really cause problems. The other thing that you all should be concerned about is safety. I heard Reza mention it today. Boeing is interested in the safety of not only the flying public, but also interested in the safety of its workforce. And so a subject matter expert named Melissa Finlay worked with another set of interns, interestingly enough, who knew how to use the tools, and they wound up going through historical data to determine the cost to the Boeing company of having incidents that were repetitive stress injuries that were caused by poor planning in terms of the assembly task. They did that extremely quickly. It was something that had never been done before, and the project has actually spread from the Everett factory on the 777 line through all of Boeing commercial airplanes factories, and it looks like it's going to spread through to all the defense units as well. Because we actually understood that, they achieved these results in all of 2 months. It was astounding to see how fast this all happened. They did really good, really top-notch work, and made fixes like this, where you started realizing that a person had back problems, and you improved the posture of the person doing the assembly task. That the person on the ladder is in a position I don't think I could get into even when I was a lot younger, and obviously has shoulder, elbow, and back problems. They just changed the position, and all of a sudden magic happened. But it had to be communicated so that something actually happened. What you're going to be finding out, as you're starting to find out in the building industry in terms of just 3D data, is that it is not always easy to gain access to data. People like to protect their data and not necessarily give you the ability to understand it. There are security concerns. You can't always figure out, well, why should I let this moron look at my data? It's not always easy to convince people to do that. There are organization, preservation, and immune response that it's not your business to try to fix my area. Data quality, as much as we love computer-based tools, is always suspect. You know, I mentioned the internet. You can read through email and understand that there's varied quality in that data. It turns out that that's true with all of the data that gets entered, that needs to be analyzed. One of the reasons that we like to put the interactive part in terms of visual analytics is that people have the opportunity and the ability to disambiguate and understand that data a little bit more clearly than computers can. Computers are not always the brightest things in the world. And we learned a lot from working with the universities. There were huge amounts of collaboration, and it's turned out to be a wonderful and fruitful relationship. And Boeing has actually hired some of the data scientist students who are coming out of Simon Fraser already. A bunch of research papers. Be happy to provide you references and connections to any of the folks that are working on that issue. So remember, I promised that this is a two-part show, right? I hit non-geometric data, hard enough to keep most people awake. Now I'll hit some geometric data, and let's talk about the problems of scale and using a field. This is also something that I helped develop called massive model visualization. And it turns out that the Boeing company has this interesting problem because it designs these complex objects that are called commercial airplanes or transports or whatever. And it turns out that those have an awful lot of parts in them. So 787 has about 200,000 unique parts, and that unique part numbers that when pulled all together, and this is excluding rivets, when pulled all together and fasteners, when pulled all together is about, a number's about 2 million. And the idea is, so is Reza still here? So Reza, you build on site. Boeing assembles its airplanes from parts that we gather from all the world in a building, and somebody talked to me about visiting the Boeing Everett site, in a building that turns out to be the world's largest building in volume by a factor of 2. And that has been true since the thing was built a number of years ago. It is massive. This is for all the twin aisles, 777, 767, 747, and the 787. It's a huge building. It's worth a trip to Seattle just to see it and take the tour. It's really fun stuff. But you assemble on site, we assemble in a building, and then build all the stuff in various places around the world. It's really pretty cool. There are huge applications, and the idea of this massive model visualization is the challenge that I laid out to the research community is, can you see an entire commercial airplane and do so and work with it interactively and dynamically? Okay, so can I take a conventional laptop, and I happen to have my laptop sitting here, can you take a laptop and actually go through something that is somewhere between 350 million to 1 billion polygons and work with it at interactive rates so that anybody who is on the design team could actually look at his or her component in real time, or somebody who's doing assembly can understand where in context his or her assembly task is, or his maintenance task or support task. There are a whole bunch of applications that are possibly anything that you can do that allows you, that requires context. If you can give them the context for a small region around that particular part, if you can give them the entire thing, give them the entire thing, then they can wander around and freely. Different tasks require different amounts of things to be able to look at. I've listed these in terms of design, everything from a design review to a parts catalog or design and context. Smaller things like parts catalogs and design and context can get away with maybe 1,000 parts. And as I said, we're approaching 1 million parts for being able to do the design reviews. And it turns out to be highly valuable at this point in manufacturing. There are no commercial tools that allow you to do this job today in terms of the large model viewing. You're essentially dealing with disk-limited sizes. I'll do a demo of an internal Boeing application as the dessert for dessert at the end of this particular section. When you're looking at tools as the way that you're dealing with this visualization stuff, you want that also to be interactive. Remember, I'm a big interactive visualization guy in terms of visual analytics. In terms of this task as well, pay attention to what the performance characteristics are. You want to load things, and you want to have this session active and working in less than a minute. You want to be able to fly at somewhere about 10 frames per second or faster. The gaming industry does it at 60 frames. For doing actual exploration, you can get by pretty well with 10 frames, and it's important to be able to graphically select and identify individual objects. There are 2 ways of doing this, as it turns out. So I'm going, anybody interested in, anybody know about rendering techniques or care? That's the bigger question. There'll be all sorts of people who will talk to you about why people draw things in certain ways. It turns out that my job and Shang Yu's job in terms of doing computer graphics and displaying things on screens is really a coloring problem. The idea is that you have to figure out what color do you want every dot on the screen to be so that you can see the right things. That's all we do. I get paid to color interactively. It's great. The hard part is that I have to do it for a lot of pixels. I have to do it for a lot of data. And I have this time constraint to do it at 10 frames per second or faster. So you probably heard the stories about GPU and Z buffers. Basically, a Z buffer allows you to do this display, and what you're winding up doing is just basically having a race to see which Z value is closest to the user on a frame-by-frame basis. It basically is taking the scene and sucking it through the screen in order to try to figure out what you actually see. The converse is to do ray tracing, and that is to basically fire a ray of light, and that's where you get the really nice-looking pictures, because you can get reflection, refraction, all sorts of cool visual effects. That's what ray tracing is in an instant. So there's some things that happen here. You can use transparency, and now these are starting to get into some images of the 787. They are part of a movie that was produced about building this thing called Legends of Flight. This is using transparency so you can understand context. That's what something of the structure looks like, so you can take a look at that. That's a detailed image. Last but not least is a 787 in flight, so you can get a good look at what the airplane looks like in a cleaned up form, and it's really rather lovely. As I said, I'm going to give you dessert after dessert because I think I'll have enough time to do so, Fred. There is a demo that I'll do, but let me give you some observations first. And this relates quite a bit to what's going on in the building industry. Boeing has designed commercial airplanes since the late 1980s in 3D. Our design has been much better because, as was described, you can understand interferences, you can reserve areas for doing design work, you can do all sorts of things that let the design happen more organically. Okay, you can get feedback in terms of the trade studies that get done. When somebody says the computational fluid dynamics is wrong, you can change it far more easily than you can if you're bending metal. What I will tell you is that the benefits that Boeing has realized by using these 3D techniques on 787, 737, some new generation of 737, the new generation of the 747-8, the 787, is that the time and cost, some schedule has been improved, but the time and cost has not necessarily been realized as much in the design process as it has in moving the results into the building and manufacturing area. Because what's happened is that stuff fits. Okay, drawings just didn't do it for making things fit. Things fit, things are correct. The first 777 that Boeing assembled actually flew. We didn't practice on anything. We didn't build styrofoam cutouts or practice airplanes as we did in the past. The other thing that's happened is that we've moved from 2D authority on the 777 because the certification agencies required it to 3D, and we're actually releasing 3D PDFs that have model-based definitions with dimensions and tolerances and all that kind of stuff associated with the 3D data. It's really pretty cool. Support is still a mix of 2D and 3D. 777 is all 2D. 787 has some 2D parts and some 3D parts. There are some caveats. Designers have to pay attention to what's going to happen downstream. It's a big deal. We are starting to evolve, and this is something you should think about, as 3D and the design artifacts become a portal into other systems so that you can gain access to a specific part or a collection of parts or a specific subsystem or the like with all this 3D data and use that to access other systems. Finally, think about this. What happens with the data over the 50 to 60-year life cycle of an airplane? Because we have to keep flying it and certified, and the issues are legion. It's not just the data itself, but you have to understand, I'm sure you understand, that as software versions change, so do the contents and of those data files that you're saving. You have to safeguard your data in terms of lots of data management problems up front, but you also have to safeguard it in terms of the longevity of the data, because at some point you may get into trouble. So think about that as you're carrying this technology forward. I would ask Sean to flip to the other projector if you would. and I'll have this demo available after my talk's over officially, and y'all can ask to take a look and fly through a 787. Somebody mentioned WestJet. My wife and I were flying to Halifax a few weeks ago, and it turns out we were sitting next to a WestJet pilot. And he said he wanted to fly a 787. So I said, well, I'll tell you what, I'll do better than that. I'll let you fly one on my laptop. He sat for the next hour flying through the darn airplane, looking at things he had never seen before, because this is the complete level of detail. So Sean, and what I'll wind up doing is flying right into the nose, which is where Bob was yesterday. And you can get an idea of what the level of detail is that allows you to take a look at a commercial airplane. Sorry, I'm not flying well here. But this is 650 million polygons in real time on a 5-year-old laptop. And they said it couldn't be done. So this is to give you an idea of what some of the complexity is. I want to honor the time. I think I've got 3 minutes, Bob. Can I fly a little bit? No, I've got 3 minutes on my clock here. But this gives you an idea of the complexity of the electrical systems that are in a commercial airplane of the 787 caliber. This is one of the 2 electrical EE bays for the 787. I'm going to try to get into the nose. So you can see not only what is involved from the pilot's perspective in terms of flying the airplane, but what's underneath, and the fun part, at least from my perspective, is understanding how it all works. And that it all works. It's really kind of amazing. And what Boeing winds up doing is that we model the airplane, and we have done more and more of this to the complete level of detail. And the more detail we get, the more computer-based analysis we can do. There's that's some of the passenger accommodations on the 787. I have not flown one yet, so if you do succeed in flying one, please let me know what your experience was like. Forward into there are a lot of features. This is a full function viewer. I'm not going through the features on it. I just want to give you an idea of the complexity of the design and the ability to democratically offer this to the 15,000 users of this software in Boeing. And those usages are increasing. As I said, we're doing it for aerospace. We're doing it for assembly. We're using it for assembly at this point with some really cool stuff that's been spearheaded out of Charleston. Underneath the covers, this is what actually gets the airplane moving. You can see the design problems. That's a whole nother talk that we could talk about in terms of design problems, in terms of space and allocation and the various effects that one can have. So anyway, that's the talk, and I'll keep flying. So thank you, Fred. Thank you, everybody.
Thank you, David. Thank you very much. I think it's all a matter of perspective. I think that with a slight repositioning, that Australian student that observed that your voice could put him to sleep could have totally turned that experience around by simply writing you a note that said, "Thank you. That was a nap I sorely needed." And you wouldn't be carrying that weight around with you all the time. Thanks so much. And thanks for the ride. Appreciate it very, very much.